Can we see okay? Yeah. Okie doke. Right, resistivity. Whoops. Yeah, I feel like I did I? Oh yeah, sorry, yeah, I'm missing one of my eyes. Let's do that again. Resistivity. Three eyes, not two. Resistivity. So we're just going back a little bit to materials and electricity. We haven't actually talked much about what gives a resistor its resistance. So for example, we've done problems in electricity with resistors. So we have our resistor here, and you know that when you pass a current through it, and with a voltage, that the resistance here, we have Ohm's law, V equals IR, so the resistance here is the voltage divided by the current, and you can get the voltage by just connecting a voltmeter around the resistor. And this here is a constant. But what we haven't really talked about is how to work out the R for a resistor. What I mean by this is before you pass a current through it, if you're making the resistor, what things affect how much resistance it has? So firstly, the length of the resistor. Do you think if I make the resistor longer, it should add or subtract to the resistance? It should add. So the first thing we expect is that the resistance is proportional to the length of the resistor. So if we double the length, we would expect to have double the resistance. So that's the first thing. Now the next thing is what's called the cross-section area. This is the area at the front. What do you think here? If I increase the area, do I increase or decrease the resistance? If I increase the area, increase it, do I increase or decrease the resistance? We've gone 50-50. So who feels really confident about their answer? And what are you saying? Increase? Increase. Third option does not affect, yeah. It decreases. Bang. So, believe it or not, when we increase the area, we decrease the resistance. So here we have resistance is proportional to 1 over the area. Now why is that the case? Because it feels like it shouldn't be, that maybe if you make the area bigger, you should make the resistance bigger. Well, the reason is this. If I go to the side for a moment, imagine I have one resistor here, and I make it twice as long, so then this is like 2 resistors of the original. Then what's the total resistance? R plus R. 2R. So if you double the length, you double the resistance. That's not surprising. But what happens if you make the resistor fatter? So you put an R here, and then you also put an R beside it. So what you have here is a 1 over R total is 1 over R plus 1 over R, which is 2 over R. So then R total this is R total, is a half R. So by doubling the fatness, we halve the total resistance. So this is why an increase in the area decreases the resistance. But of course there's another variable that affects the resistance as well. Heat, yeah, but like I said, this is before we turn the resistor on. Like we're manufacturing it. Yeah, but what the heck is that?
The material.
The material. Yeah. So, of course, if you use copper, you'll get lower resistance than if you use something like a plastic. Yeah. So there's a third variable here, which is to do with the material, which is just a constant, and the name of this constant is the name of the lesson, resistivity constant. So in other words, putting these all together, we get R equals rho resistivity times length over area. So this here is the total, this here is the length, this here is the area, and this here is a constant due to the material constant. Yeah, it's different for each material.
Is there a special name or just material?
Resistivity constant. But I'm just explaining that it's a constant for the material.
That's correct.
Yeah, looking at this formula. So let's have a look at an example. Oops. Okay. Can I scroll down now? So this is the formula which you need. Yep. Okay. So something like nichrome. This has a resistivity constant of, let me get it here.
Nichrome is nichrome.
Yeah. Yeah. What? Oh yeah, okay, sorry. I don't know what things you do in chemistry or not. Is this a new thing for you then?
I've never heard of nichrome.
Yeah, again today with the listening, would you care repeating for Joshua?
Nichrome is nichrome.
Did you get that? Yep, great. If you needed it provided, yes. Yeah, the focus, back here please. Right, so nichrome, oh yeah, actually I didn't say what the unit here for the resistivity is. So let's actually just get the unit before I go ahead. Yeah, so resistivity would be RA over L. The unit for resistance is ohm, and the unit for area is meter squared, and the unit for length is meter. So the unit is ohms meter. Yep. Okay. Right, so for nichrome, it is 1.1 times 10 to the minus 6 ohm meters. So let's imagine we're making our resistor. So let's give it a length of, it's not going to be that big, it's only going to be like 2 centimeters or something. And if I look at the face here, the face of it will say has a radius of 1 millimeter. I know that's a bit too small. 4 millimeters. So what I would like you to do for me is to calculate what the resistance is here. So I would like everybody to calculate the R, the resistance for this resistor.
pi squared?
Yeah.
Moving to the formula for area and formula.
No. No, you don't get, as far as I remember, you don't get any area or volume formulas. Except possibly for the sphere. Maybe for the sphere. Millimeter is to the minus 3. Yeah, well, I made this resistor tiny. It's only 2 centimeters long and 4 millimeters wide. Now, actually, by the way, the reason that this is so small is it's not really a resistor because nichrome is actually a good, well, it's not a good conductor, but a reasonable conductor. Okay, so you know it's more of a, think of it more as a component of a machine than actually maybe as a resistor. Anyway, you have a really small number, is it? So let's calculate it. It is rho L over A, so that is 1.1 times 10 to the minus 6 times 0.02 all over pi or squared. So what did we get here?
0.438
0.4, yeah, roughly 0.4 milliohms. Yeah, so it's tiny really. Okay. Can I give you another example? Yeah. I can scroll down? Okay. By the way, I want you to remember this, not remember it for the exam, but just remember this number for the next question, okay? So for the next question. So what we have here is we have a very fine wire. Its radius is only 1 millimeter, but it's quite a long wire, so we'll say its length is 1 meter. Now, when we pass a current through it and a voltage through it, we notice that the voltage drops a little bit. So I mean, there's no resistor here, right? It's just a wire. But what you didn't really notice with the Ohm's law experiment is you always have resistance. There's never such thing as no resistance. So there will be a tiny, tiny drop in the voltage here. Okay, so what we'll do is we'll say there is a voltmeter connected up here across the wire. And let's say the voltmeter reads a very, very small drop in voltage. Well, no, let's not make it too small. Let's say it's 0.1 volts on the voltmeter, and there's a current going in here as well. Yeah, let's just say that the current is quite small as well, 0.1 amps. No, yeah, okay. And the question is, so forget about the nichrome constant, I'll do another one like that later. The question is, calculate the resistivity constant for this material. So here my question is, what is the resistivity constant for this wire?
3.145 times 10 to the minus 6.
100% sure? just give it a minute. So here we have V equals I or. So or equals V over I, which equals 1 ohm. But you also have or equals rho L over A. So therefore, rho L over A equals 1. So then that means your constant is equal to A over L. So then the constant here would be pi or squared over the length. So that would be 3.14 micro ohm meters. You got that also? Yeah? Okay. So my next question, we'll use this one as well. So this wire is a little bit like a small resistor. It's not losing much voltage, it's losing a little bit of voltage. Well, actually I said it's a small resistor. I guess the resistance is quite big. 1 ohm is a lot for a wire. Anyway, where is this lost energy going when it loses this heat? So this voltage is being dropped because there is heat energy coming off from the wire. And in fact, last year the students broke the variable resistor because they got the battery on and the wire slowly heated up until it snapped. Okay? So in fact you can, if you leave this on long enough, you will feel the heat coming off and the wire might snap. Okay, because it will, as you know, as it heats up it will expand. So then if it expands enough it will snap, it will break. So my question is, if I leave this on for, let's say 2 minutes, how much heat comes out? So I want the heat energy that leaves this if I have it on for 2 minutes.
Energy power
Yeah, but you don't know the power here. But yes, but you can work it out. Yeah, so you can do it this way, and you can energy is power multiplied time. Yeah, it's not that much, is it? Is that only 1.2? No. Did you forget about the time? 1.2. Okay. So let's have a look here. You have power equals work over time, so then the work, which in this case is the heat, that's power multiplied time. But there's another formula for power. What's that? IV. So you end up with this formula, Q equals IVT. So that is, let me see, that's 0.1, 0.1 and 120. So yeah, it's only 1.2 joules of heat. So nothing really. Okay. Let me give you another one to try here. So this is what you can actually do as an experiment to calculate this constant. You see that? You can actually do this as an experiment to calculate the constant. So if you're doing it as an experiment, rather than having one value for V and one value for I, you do it many times and get different values for V and different values for I. Okay, so let's say here, this time we have 2 meters of the wire, and here's my table. Here is voltage in volts, and here is current in amps. Okay. So the voltage we increase it 2, 4, 6, 8, 10. So we have some way of increasing the voltage. We could use like what we did in Ohm's law, a variable resistor, it doesn't matter. And then we measure different currents. So we have, I'm going to do this in milliamps, by the way, milliamps. Can you change that in your table to milliamps? So 75 milliamps, 164 milliamps, 230 milliamps, 312 milliamps, and then 418 milliamps. So firstly is plot I on the y-axis versus voltage on the x-axis. And then 2 is, let's say, estimate or from the graph in 1. And then 3, use the or from 2 to estimate the resistivity constant. I'm getting there. You need to know the area. So what I'm going to do here is give you the diameter. I'll say the diameter is quite small. Let's say 0.2 millimeters. That's the diameter. Okay. So I'll just give you a minute to try that, and then I'll do it on the board here. Of course, you should change milliamps to amps, and you should change millimeters to meters. On the graph, it's not necessary, but for your calculations, yeah.
We still have to do the graph.
Yeah, because, yes, please do what I asked you to do, in other words. And by the way, I've seen this type of question in section A and B. Although if it's in section A, you're not expected to be maybe as accurate as a section B question where you should use graph paper and draw it very, very neatly. Finished, Tanis?
No, I'm on the end of the page. I have no page to write.
So rather than just sitting there lost and confused, why not ask someone for paper? Just an idea, you know? Just as strong?
Give us a bit more time to finish all the questions.
What's that?
Give us a bit more time to finish all the questions.
For this one?
Yeah.
Okay, which part are you on?
I just do the count.
Okay, fine. Joshua, have you finished this? Did you draw the graph?
That's all I have.
You're done? Don't take this the wrong way, but what's up with you this week? I mean, you're having trouble with your factors, which you've done in physics, you're not listening to me in class, and you know perfectly well how to draw a graph, since you've done it like 4 times in your 4 lab reports. Look, let me break this down for you, Joshua. See here? I on the y-axis, V on the x-axis, here is I, here is V, there are the numbers, there are the numbers.
Is there going to be 0.2 mean is this the one there?
Yes, that's what I said, and I give you, hey, Kendall, there's a clue here. I drew it, and I wrote D. That was my hint that it was diameter, by the way. It seems some people have decided to take their Easter break sooner than others, at least mentally. What's that, Joshua?
Is resistance meant to be very, very small? Not very, but quite small. Because it's just a wire.
Yeah, it's just a wire, a nichrome wire, I think it is. It should be less than an ohm, possibly. Yeah.
The R function or average?
Average, so to speak, estimate from the graph. Okay. Do you have a value for it, Tal? Do you have resistivity constant?
Yes.
Yeah. Let's have a look at this though. So my first job, I'm putting voltage on the X, current on the Y, but the current is in milliamps and the voltage is in volts. Right, so this goes 2, 4, 6, 8, 10, and then here milliamps, 75, 230, sorry, 164, 230, 312, 418. Right, so let's graph this. Scatter. Okay, so don't display that and give me X and Y. So x-axis is voltage in volts, y-axis is current in milliamps, and the graph, the title is current versus voltage. Okay. So let me just shrink this a little bit. Now, in the exam, how are you to get the slope here? Because if you remember, when you did this in Ohm's law, here is V, here is I, V equals I or, so or equals, So then I equals 1 over R V. So then the slope equals 1 over R, so the R is 1 over the slope. But this is exactly what you did in your Ohm's law, lab number 3. So my question then is for the exam, and how do they want you to get the slope from this?
The difference in y minus the difference in x.
Yeah, but what y's and x's?
And the difference in left.
Not this, no? Well, first, actually, let me just put in the line.
Shouldn't they make a change?
Yeah, this is what they like in the exam. They want you to put in a triangle. So what I'm going to do is, I'm going to do it like in the exam. If I look at my triangle, I'll use the point furthest away. So I'll use this point here, and then this point here. Now, these aren't points on my data. See, I start at 2. So this is actually my first point. But they don't like you using actual points, they want you to use the line. So can you just, it's more accurate, especially if these points don't all go on the line. What's that?
So you put a point on the line.
You wouldn't get full marks. What's that?
So you put a point on the line.
That is exactly the opposite of what I'm saying.
The point is pointed right.
Yeah, you're right. Yes, you're right. You want pick a point on the line other than the points given, and preferably furthest away from the center of the line. So roughly, where does this point cross the y-axis? That is at about, now if you had graph paper you could do it neatly, but 20. So my first point is 120. Yes, Tamish.
In case of there were no graph paper,
there will be graph paper. There will be graph paper. There will be as much graph paper as your heart desires.
And what if it was section A?
But there will be enough graph paper. If you want to use graph paper for section A and B for every single question, it will be provided. Okay. The last point is 11 and 440. I don't. Is it exactly in the middle?
Yeah, use your arrow to check that. See? Exactly how, and then lift it up. Yeah, it's good.
You feel confident about that?
Okay, take 48.
Oh, this is better, yeah, because now it hits exactly at 450. So 11 and 450. Okay. So the slope is 430 over 10. Yeah? 43. What? Listen to this, please. But you're going to see my answer now in a minute. Can't you wait? It's not that exciting. So what's the or here? It would be 1 over 43 ohms. Oh wait, no, it's not ohms, because remember we have V equals I or, so or equals V over I, but the I here is in milli. So I should fix that first. Let me just go back a bit here. This is 430. This is milliamps. And then here it's 10, what's the unit? Volts. So then the M, 1 over M is 10 volts over 430 milliamps. So this is 10 over 430 times 10 to the minus 3 amps. And volts over amps is ohms. So hang on, that cancels that, and we get 10 to the 3 over 43 ohms. Okay, so can you tell me what this is in a decimal, please? It's going to be 1,000 over 43. What's that, roughly 210? That's off by decimal place. 20. Okay. So that's the resistance. Now, it's not quite the first one. It is quite big, isn't it? So,
For a while. 23 ohms.
it is, but like I said, the material nichrome is a conductor, but it's not a great conductor. In fact, nichrome is what's used in electric heaters. So if you have enough of it, you can actually get a good bit of heat from it. This is the correct answer.
Are you sure?
Yes, because my numbers are very similar to question 1's numbers, and the answer in question number 1 is 23.3. And I used nearly the same numbers. I just changed the length a little bit.
That's great.
What came out as 27? For OR? You got an OR of 27? That's too big of an error for the exam. For the exam, by the way guys, if you wanted full marks in the exam, really I would only accept answers between 22.26 and 24.26. For this type of answer, I'd give you plus or minus 1 ohm. 27 was way off. I'm sorry, you wouldn't get full marks for that. It's too big of an error. Okay, the last part, you have OR equals rho L over A. So rho equals OR A over L. So rho equals 23.26. What was the length? Was it 2?
Yes.
And what was the diameter? 0.2 millimeters. So the radius is 0.1 times 10 to the minus 3 squared. Okay, so type this in and tell me what you get, please. 3.65. 10 to the minus 7, is it?
Yes.
Ohm meters. So that would be 0.365 times 10 to the minus 6 ohm meters. So the answer is 0, should I do it in milli or micro? Doesn't matter. 0.365 micro ohm meters. So really, it's not that difficult. You have really one formula, and you just need to remember your formula for the area of a circle is pi r squared. You also may need to use Ohm's law, and also maybe law about power is work over time, and power is IB.
Will it be a question from this section?
It would only be part of a B section. Like for example, do you remember we did the Kirchhoff questions? What I'm imagining is in part A they'd ask you to calculate the resistance by using this formula, and then part B they would say this resistor is put into the circuit below. Use Kirchhoff's rule. So if it was in section B, it would only be part to lead you into something bigger. It's more commonly a section A question.
Like that long?
This would be a long section A question, but really, if you look at these questions I gave you here, I think I took all of these from section A possibly. Although some of them might have been a section B where I cut out part C and D. But I think a few of these are section A. What's wrong? Like for example, if you look at number 4, see number 4 there? That's definitely a section A. But if you look at 5 and 6, there's section A also. It's just question 1, 2 and 3, no, 2 is section A. Question 1 and 3 I may have possibly taken from part of section B.
If it was a part of section B, how much is
Marks you mean?
Yeah.
I think number 1, what we just did, would probably be 6, maybe 7, 6 marks.
So it's like a part of section B.
Yep. That is exactly what I said. Good job. Yeah. So is this really, are we really thinking about holidays starting Friday? Is this a big distraction for everybody?
Very.
I'm talking right now and all you're hearing is holiday, 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 like what? Right, we'll finish there. So I have some of you later for tutorial in maths, don't I?
Wow.